Hello everyone, I'm very happy to be here today. My name is Kyo. I'm here to present the paper called Tablets Folder of Documents, Page Stream Segmentation of Business Documents. This is a joint work with Yusin, Nisak, and Odo. Here's the outline. I will start with the introduction and then with the research questions, the datasets, results, and finally the conclusions. So our task is, as the title suggested, to perform page stream segmentation, or PSS, of business documents. Imagine in the legal settings where all documents belonging to a single case are often bundled together. Or in the business settings where companies might sometimes use bulk scanning services to convert the paper documents into the digital files all in one go. The process of separating the documents into different groups is required before each document is fed into the pipeline for information extraction, because what information to be extracted is based on specific types of documents. This leads to the task called page stream segmentation, or PSS. Basically, if we have a bunch of pages in which we call a folder, we will train a model to segment this folder into separate documents as shown here. We are under the assumption that the pages are sorted, so there's no page from different documents interlacing each other. So in order to segment a folder, the model must specify the location of the breaking points. The breaking point is defined to be the beginning of the document, so it indicates the boundary between one document and another document, as shown here. The location of the breaking points can be written as an array consisting of zeros and one, as shown here, where 1 means the breaking point or the beginning of the document and 0 means non-breaking point or the continuation from the previous page. Therefore, the task becomes binary classification. Another point to note is that we don't have the predefined categories. For example, we don't know if documents contain emails, receipts, or something else. So, the model must compare the current page to the neighboring page to decide whether or not the page is a breaking point. The evaluation measures for the PSS task that we'll use are F1, precision, and recall, because it is a binary classification task. And we also propose the new metric called the minimum number of drag and drops, or MNDD. This metric is designed to be more user-centric. Let me illustrate how this metric works. Given the interface, where a user can freely drag and drop a page into the correct document, the MNDD is the minimum number of drag and drop action required to correct all the errors from the prediction. That means the better model will have the lower MNDD. For example, in the picture here, we only need to drag the pink page here into its correct position. So the MNDD in this case is 1. While in this picture, we need to drag the blue page here and the yellow page here into their correct positions. So the MNDD is 2. The MNDD metric is aimed to measure the user satisfaction of the system. Here is our model. The input is a folder, which is an array of images from documents. Then these images are fed into the optical character recognition software, or the OCR, to extract the text and the bounding box positions. At this point, we have the image information as pixels, and the text with layout information as tokens. The images above are to be input to the ResNet model to extract visual embeddings depicted by the pink array here. while the text and layouts from the OCR are input into the layout element model to extract textual embedding, which is a bool array here. Then the two arrays representing the visual and the textual embeddings are then concatenated and fed into a series of one-dimensional convolutional layers. The convolution operation is done along the series of pages, so this allows the model to learn the similarities and differences of a page in comparison with the adjacent pages. For each page, the final output is either 1, which indicates that the page is a breaking point, or 0, which indicates that the page is not a breaking point. Moving on to the research questions. The first research question is obviously, how does the proposed model perform on this task? And we want to know if both textual and visual information are necessary. So our second research question is, what is the contribution of the ResNet and the layout element components? And lastly, for the third research question, we investigate the potential biases of the model. Are there any biases in terms of the position of the breaking point in the folder, the length of the folder, or the length of documents in the folder? Since we could not find a large enough public dataset for training and testing our model, we generate a dataset called tabme, which stands for Tab This Folder of Documents. The dataset contains documents randomly merged into folders. Documents that we use are from the publicly available Truth Tobacco Industry Document Archive. Our dataset is currently the largest public dataset for the PSS task, with around 120,000 pages, where the previously existing one used for comparison, which is called Tobacco 800, contains only 250 pages. The number of documents in a folder is randomly selected according to the Poisson distribution, with lambda equal to 11, based on the observation that we have in our applications. And the documents are split into the training, the validation, and the test set by 90%, 5%, and 5% respectively. Here is the statistics of the dataset. Documents are merged into 100,000 folders in the training set and 5,000 folders each for the validation and the test set. Each folder contains around 30 pages on average. The histogram showing the distribution of the folder lengths are shown here. Here is the sample pages from a folder. As we can see, the first 3 pages belong to the same document, while the last page is from another document. We might need help from both the language model and the image model to predict the correct segmentation. To answer the first research question, we measure the performance of the model on our tabme dataset. Our model achieved the MNDD matrix of 3.44, which means on average, it takes only around 3 drag and drop actions per folder to correct the errors of the model. We obtained the F1 GB 0.953. Since there's no previous baseline on our dataset, we compare against the 2 trivial models. The first model makes a prediction randomly, so we will refer to it as the random model. And the second model does nothing rather than make an obvious prediction that the first page in the folder is a breaking point. The performance is shown in the table. We can see that our model outperforms the trivial baselines by a significant margin. We also compared the model against the baseline provided by Rudiment and Heyer in 2019. This was measured on the smaller Tobacco 800 dataset, which contains only 250 pages of documents. The previous work used accuracy as an evaluation metric, so we'll use just that as well. The result is shown here. The second research question is what is the contribution of the ResNet and the layout element components? As seen from the table, when considering the F1 score here, the score drops slightly when we exclude layout element, which is a language model that also takes into account the information of the document layout, and the score drops greatly when we exclude ResNet, which is the image model. Therefore, the image component plays more significant role in this dataset. Moving on to the third research question, we consider three potential biases. The first bias is the page position. Let's have a look at the graph on the left here. The y-axis of the graph is F1, which we use to measure the performance, and the x-axis is the bias that we consider, which is the page position. The pink dots show the performance of our model. It can be seen from the graph that the performance is roughly constant regardless of where the page is within the folder. The second bias is the length of the folder, shown in the graph at the center here. Similar to the previous bias, the performance of the model is roughly constant. But when comparing against the random prediction, which is the blue dots here, the performance drops when the folder gets larger, which is to be expected because larger folder means more chance for the model to make mistakes. And the third bias that we investigate is document length. As we can see, the performance of the model is pretty consistent for the short documents in this region and the long document in this region. In conclusion, the work presents the TAPME dataset generated specifically for the page stream segmentation task. And we also propose the metric for the task called the minimum number of drag and drops, or MNDD, which is aimed to measure the user satisfaction when using the model in the real-world setting. We also propose a deep learning model for this task based on ResNet and layout alone, and perform a Bayesian study to measure the contribution of the image and the text input. And we also evaluate the potential model biases. The take-home message for this talk is that without textual and layout information, it's not enough for the PSS task, because the model needs the image information to increase performance. Finally, for the future work, we will tackle the more complicated version of the PSS task, where the document pages are shuffled, so the graph neural network might be the possible solution. That's the end of our presentation. Thank you very much for your interest in our work. It was a big honor to speak here today. Thank you again.